what our topic is today. It's really supersizing your data for turbocharging your performance. I hope that you don't think that supersizing means somehow you have to make your data bigger. It just means that you got to give basically your data some superpowers so that your data actually drives your performance. A lot of people, including myself, have sometimes come to you and shown you how to tune your models. And now I'm taking a slightly different approach, and I'm trying to improve or create libraries for data. So please join me in this journey. So, how can we make data science better? This is your typical data science, workflow. You start with the data, you understand the data, get some business domain experts together, or maybe your data scientist itself is a domain expert, and you try to ask questions about the data and try to understand what it can give you answers for. And if you spend a lot of time on the data, you then get to know some of its weaknesses, where it's good and where it's bad, and then you start to remove each one of those weaknesses through data preparation. And once you have your data quality improved, you go into model building, and then you spend hours, days, weeks, months on model building. Compared to a lot of studies that show that data preparation and data wrangling takes almost 80% of a data scientist's time, I see still a lot of data scientists spending less time on data because they think that's more the job of the data engineer, and spending more time on model building and then model tuning, testing, and deployment. And so my belief that is now that you should spend more time on data understanding and data preparation. And in this particular chart that you see a lot, you do see some mistakes or some things that are missing. What are the steps that are missing? Number one is there's no mention here in data preparation of feature engineering or feature selection. A lot of it is just glossed over. People don't do much feature selection at all, in my experience. They take the entire data and feed it in. And so I sometimes feel like that's crucial step is missed. The second thing that people miss is data visualization and data quality assessment. People don't really run their data through some data quality checks to see how good is their data. And I feel like a lot of people go straight into modeling or straight into data prep. So that's another missing step. The third is model troubleshooting. A lot of people don't know why their model is performing poorly. They just double down on the same model and tune some very complex model for days, weeks, and months. And I feel like that whole approach is somewhat inverted, where you should be spending more time on feature engineering, feature selection, data quality, and data visualization. And the last step is model serving and pipelines. People spend an enormous amount of time model serving and pipelines, while they could be spending more time, I believe, on the first two steps. So with that, let's try to come up with any, what are the reasons why people are so focused? The reason is the AutoML tools, some of which I have been part of and developed myself, have been very narrowly focused. You spend hours, sometimes weeks, tuning a model in an AutoML tool. And I remember one time uploading a model, a data with about 300 rows or something, and the AutoML tool ran for hours. So you can imagine if you had sent that AutoML tool, a million or so rows, it may run for a couple of days. So if you were to find that it's not even meeting a logistic regression or even a gradient boosted tree, you have really spent way too much time on AutoML and way little time understanding about your data. So here's an idea. Instead of spending hours tuning a model, how about if you spend a few minutes tuning our data for better performance? So this was an idea that is not new, but sometimes you have to stop and think about it. So I decided to introduce a better approach to data science workflows and how to supersize your data. And first and foremost, I've created two libraries for data visualization. I've got a couple of libraries for feature engineering, feature selection, some model troubleshooting as well, which I'm going to show you, and then model serving and pipelines. So first and foremost, what are the two new libraries or existing libraries? AutoViz, if you've not seen AutoViz, I'd like to introduce it here. Pandas-dq is a new library that I've created, and that library is under development by me, and I'll show you some of its new capabilities. The second one is lazytransform. Lazytransform is another library that will, one-click transform all your categorical and NLP features into numeric features. And featurewiz is another library that I created for feature selection and feature engineering. So there are two libraries right now that you can use today to do feature engineering and feature selection. And that, to me, is where we should be spending a lot of time. In model troubleshooting, there are two ways to do model troubleshooting, and I'll show you that through the new class of models I built. They're called Sulo models. Sulo stands for super optimized or super learning optimized models. These are a new class of models called super learners. And these super learners basically take existing models and they kind of put them together in different ways in order for you to troubleshoot these models better. And I'm going to show you how it works. And finally, model serving pipelines. We're not going to show that today. Called Deep AutoML is another library that I've developed. But if you want to know how to serve models in one click, or to build models, deep learning models, Deep AutoML is I've done a session separately for AI Camp. So if you go to the YouTube page of AI Camp and look for Deep AutoML, you'll see that I've made a presentation last year about this. All right, so let's talk about how does this process work, this new supersizing your data for better performance. You all want to know, how do I use this, right? So the first is you can use AutoViz for EDA and insights. Try to just get a quick understanding of your data. Second, you can use pandas-dq, the new library for data quality and preparation. And three, you can use featurewiz for feature engineering and selection. And then finally, you can use lazytransform for finally one-click transformation of your data to all numeric. And then you can use it for what I call super learning models. And those models can also be used for troubleshooting what's wrong with your data, which is a very new insight I've developed, which I wanted to share with you. So I'll take a couple of questions while we wait. Let's see if are there any questions? Okay, all right, so right now, no. So where can you find these libraries is the next question that probably comes to your mind. And AutoML is a library or a GitHub that I created, which has all of these libraries in one place. Like I mentioned, it's got AutoViz, AutoML, and AutoTS for time series, featurewiz for, like I said, to feature selection, pandas-dq for data quality, and for deep learning models, Deep AutoML. All of these libraries, different kinds of them, will support text, image, tabular, time series, and NLP, and all of that. So you want to be able to come to this GitHub and be able to look at all of the different things it can do. I've also integrated it with some MLOps platforms like Orchest.io, MLflow, Docker, so you can actually put them into production. And finally, we have a large set of active community members for this GitHub who will, answer your questions, solve the issues, and so on. So if you haven't taken a look at it, I, request you to do a Google search and find this GitHub. Now, you might be wondering how much of this is driven by just one man's, or one person's view. It's not really one person's view that these libraries are useful. I'll just give you a list of research papers that already use featurewiz. And this is just from page 1 of a Google search that I did before this presentation. I just typed featurewiz in a PDF and basically gave me a whole bunch of research papers that use featurewiz. I've gone through many of them in the past, because every time a new one comes up, I usually go read the paper that how do they use featurewiz. And so you can see that that's just page one of Google search has already got 11 papers. And here's a paper that actually says it uses featurewiz in its title. So you can't get better than that credit in terms of just how much the PhD, the research community uses the featurewiz library for feature selection. I've got lots of other blogs on AutoViz and featurewiz. There are hundreds, if not thousands, of notebooks in Kaggle that that actually use all of this. So I'd like you to spend some time learning about this if you've not heard of it. I'm not sure if the checks and balances question is for us. All right. Now, in terms of AutoVML, the GitHub, what are the different things you can do with it? One, you can do data insights, data quality, feature engineering, like I said, one-click transform, and then model troubleshooting, super learners, deep learning models, and interpretable models. So these are, and time series data. These are all the things you can do. We're now going to go to the demo and start looking at how we can use these libraries. So let me go ahead and
Hey, Ram, before you go to the demo, I see a couple questions in the chat. I'm not sure if you answered or not.
yeah, no, yeah, that's why I was looking for them. So let me share the links in the chat. Yeah. So I have not gotten the links yet. I will send everyone the PDF through Bill. So if you can send it to everyone, it'll be great. So if everyone can just click this Kaggle RSesha code, that's where all of the notebooks for today's session, the demo notebooks, are saved. So they have a special name. So I will show you that. So if you can please click this link, everyone, RSesha Kaggle.com, Kaggle.com/RSesha, you'll get to this web page. And now we will see how it looks. All right, so this is my web page on Kaggle, and I've probably got a few hundred notebooks, and those notebooks are meant to showcase how to use this library and the libraries that I've developed. So we have what I call AI Camp Special notebooks. These are the top notebooks that I will be discussing today. There are hundreds more notebooks that I've done, but for now, let's just go one by one, and we can see how it works. All right, so if you look at the AutoViz library, which you may or may not know, is got about 2 million downloads, and it is a very popular library for automatic visualization. I've introduced something new in it, so today I want to share that with you, and that is your AutoViz now can also do data quality analysis or give you some cleaning suggestions. So we are going to produce in AutoViz a new setting called verbose equals 1. So if you've tried this before and now you've used always verbose equals 0, now we are going to set the verbose equals 1, and you're going to see something new in AutoViz. You're going to see a new data cleaning suggestion table. And in this table, we are going to show you how various features have some data quality issues. The first one is this one. It says unnamed 0. Sometimes this creeps up in your tables, and this is possible ID column or a useless column you can drop. So it finds that the brand variable has some rare categories, and then it finds that mileage has a highly skewed right distribution, and so you need to do a dropping outliers in this or box transforms, and take a look at the number of nulls. All of them are 0 here, so that's good. So you get a quick understanding of your data in addition to the charts you all know and use. So that is an important one. In addition, it found that there was a NLP feature or a model word for the cars models, and so it automatically did a word cloud. What's important about this word cloud is that you can see that there are models like Rogue, Nissan Rogue, Durango, which is a Dodge Caravan. These are Ford Fusion model names here. But you also notice that there is a word called door that's occurring repeatedly. So if this is something that's not a model word, you should clean up your data. And that's what you're able to quickly find things like this in AutoViz, which you were not able to do before. All right. Any further questions? Okay. All right. So let's go to the next tab. I'm going to be switching tabs here. The first one is called the AI Camp Special AutoViz. The second tab is AI Camp Special Data Quality. I mentioned to you that I've developed a new library called pandas-dq. So in pandas-dq, we can take a train and test data set. In this particular case, I've taken the housing prices data set. It's got 81 features, including the sale price, which is the target feature. And you can see here that it's got a lot of categorical, it's got a lot of nans, it's got a lot of numeric values, numeric features. You want to be able to quickly understand what are the differences between train and test, because one of the first things you need to know is this thing called test train skew or test train drift. And you want to see how different are the two data sets. So we're going to just pip install pandas-dq from the GitHub. And from there, we're going to download or import a few libraries, a few modules. One is a fixed DQ, the DQ report data schema. I'll explain to you each one what it is. Give it the name target, and the remainder are predictors. And now the first thing we're going to do is what is called a DC report. A DC report is a data comparison report. You can use it to compare train and test data, and you can exclude some variables that are in train but not in test. So you exclude the target variable, and otherwise it'll say that these two data frames are not equal. But in this case, these two data frames are equal except for the target variable. So we're going to exclude that from analysis. And then we're going to say verbose equals 0. You will quickly get a huge printout or HTML file or inline report that gives you all the differences between train and test for each variable. And this is very important because we're going to see here that one particular difference is very, very dangerous, and that's this one. We found that the percentage of missing values in this variable called basement half bath is different between train. Train had 0 missing values, but test had 0.14% missing values. That means you have a skew between or a difference between train and test. While train had no missing values, in test you have missing values. So let's say you fixed all the missing value problems in train, but you forgot about test and you thought that would be clean. Now you're going to find that when it runs in, when production gets in, right, when you deploy the model and you've got no fix for the missing values of basement half bath, because you assume that all of them are fixed in train, you're going to find that it blows up. So you need to be able to understand that the difference between train and test or between inference time and training time are very significant. And unless you have a library like this, you won't be able to detect them. So we're going to fix this. And how do we fix this? We're going to use fixed-dq, which is a module within pandas-dq, and that shows you that it's going to drop certain variables that have more than 80% missing values. If you have more than 80% missing values in a particular feature, it's probably not that useful. But you can see quickly that after dropping those, it cleaned up your data set. And we're going to see how well it cleaned it by comparing the two data sets after they are cleaned, X-train T, X-test T, or the transform data sets. We're going to compare that in using data comparison report again. And now we are going to find that the distribution differences are very minor. There are very few problems in this column, distribution difference. Now let's take a look at one more issue here. We found that within this distribution report still, there is a data type of basement full bath is different between train. In train, it was integer 64, in test, it was float 64. How do we fix that? So once I have another module called data schema checker, you can take the train schema and you can put that into your preferred schema, and you feed that to data schema checker, and it'll actually learn from train, and it will pass along that schema to test, and you're going to have this or any of the differences between train and test, between integer and float being fixed. So all of the test variables will then have the same schema as train variables. So now when you run the DC report again, all those differences are gone. You can see here on the right, the distribution differences are all none. There is no difference, except now we have a few percentage of unique values. The unique values will always be different, but this is just a highlight. And then there are some distribution with a KS statistic that I show you. And these are things that you need to look out for. Finally, you can also run a quick data quality report on train. Let's say we run a data quality report on just train. It's called DQ report. You're going to see that the data quality report tells you that Ali has got 93% missing values. So that's a red flag. And you also have fireplace in and a few other variables here. So let's say after data cleaning, how does the data quality report look? So we take the X-train T, which I told you was the transform data set, and we send it to data quality report. And you can see that all the missing values are now gone. And this is a pretty clean data set. So this is how you find issues in your data and fix them. All right, so let's take some questions. Yeah, so very good question, Parnika. In terms of categories that are present in train but not in test, you have that in the percentage of missing, in the percentage of unique values column. If you have, let's say, one of them being 1%, the other being not 1%, then it is a problem. But I have stayed away from looking at categories because the number of categories can be very large. But it's a good idea. We can probably look at that. And the second question you asked, Parnika, was about the threshold of missing values. I currently have set it at 80%. You can have it at 90%. You can have it at 70%. But that's something that I can make it into a defining argument or input. Any other ones? Okay. All right, Tim. Question? Can you unmute yourself or post it on the chat? Sorry. Okay. All right. Next, that's a good idea, Parnika. We'll definitely, if you can send me a note, put it as an issue in the GitHub, I'd be more than happy to remember to take care of it. All right. So the next question. All right. The next thing we're going to do is we're going to take the AI Camp Special Housing Part 1, and we're going to look at, how do we take a Kaggle data set that's like this housing, and how do we get a high score, which is probably why you are interested in. And we're going to try to use a couple of libraries to see how, with like 5 lines of code, you can get a very high score. So first, we're going to use lazytransform, which is basically going to convert all your numeric features into, convert all your categorical and string variable features or object features into numeric. And then we're going to use another library called featurewiz to select the best features. Now, as I mentioned earlier, this housing data set has too many features, and many of them may be redundant. So you want to be able to test and select the best features. So we are going to create some additional features, which is, I've just taken you as an example to show you what you can do. Let's say we create some additional features, but what if these features that you've created also have multicollinearity, meaning they are highly correlated to each other? Then you're better off than running it through featurewiz. So first you create your extra features in train and test, and then you come to featurewiz. And that's where we are here. We call featurewiz, and we don't have to tell it what features, how many features, nothing. It takes the dirty data as is, and it converts them all using its inbuilt category encoders, and it creates numeric features out of them. and then it's runs two methods called Sulo. You need to go to the website to know what those are, and then it uses recursive XGBoost, and it cuts down the number of features. And you can see here, it gives you lots of charts. It found 48 important features, so it already cut the number of features down by 50%. From 80 features, you're down to like 40 something. Now we are going to take these 40 features and we are going to transform them because it only selects features, it doesn't transform them for you. Now we are going to use lazytransform, and we're going to also see that the target variable is highly skewed. After 40,000 or 400,000, the target variable has some houses that are under 700,000. So we are probably better off using log targets. So we're going to transform the log, lazytransform as a regressor for log transformation. It's called XGBoost regressor. It actually does the prediction for you. So all you have to do is once you transform your data set with lazytransform, or once you've selected your features, you just need to call XGBoost regressor, and it will run and select the best model for you, tune that model, and then if you submit this model, you can see the predictions for the model are very similar. It's about 500,000, and then you get a score of 15,000. Now you might say 5 lines of code, 15,000 score is good, but can we do better? So we are going to see how we can do better in the next step. All right, so now you go to the next notebook called AI Camp Special Part 2. All right, any questions further? All right, there is a question. Feature engineering. Right. So the question is, people do use synthetic data. I use them in forecasting, for example, because customers do not want to give us their transaction data, or do not want to give us their point of sale data. So we do use a little bit of synthetic data in order to build a model, but we then turn the model over to them for them to run it on their data, and then we find out what their challenges are, and then we then get the model back, and then we fix some of those issues. I have not been using synthetic data to build a model, or synthetic data to do any kind of EDA, because it does not make any sense to use synthetic data for those things. But synthetic data, I use them for building a model when the customer cannot give us a data. We use the same column names, we create some synthetic data, we build a model, we then make some recommendations on how to tune the model, then we send it to the customer. So that's how we use it. All right, hope that answers your question. Let's go to AI Camp Special Part 2. Here you can see that we are going to use pandas-dq first to fix the data quality issues in the housing, and that's what we are going to do. We pip install from the GitHub, and we also similarly use featurewiz and lazytransform. But first we do data quality check. Like I said earlier, we do the DC report, and then we drop the few columns, like 4 or 5 columns I mentioned, and then we now use same as before. We use feature engineering to create some additional features in housing data, and now we do feature selection. And now how many features do we get? We get only 43 features. Previously we had 48, and we use the same XGBoost regressor. And what is the score that we get now? So we now get a score of 14,760 in Kaggle after fixing data quality. That's a 1,000 point drop in your error metric, which means you get a much higher rank in Kaggle. So this shows that how you fixing data quality with 1 or 2 lines of code in the very beginning, how it can improve your model performance, and how feature selection and all of that can improve model performance. So this is kind of a big, a small example, but a big deal in my mind in terms of how to use all of the libraries that I mentioned. Now, a lot of you are interested in feature selection. So I'll just do a AACamp special on feature selection methods. You might have heard of multiple libraries that do feature selection. I'm not going to compare most of them. One is featurewiz, the library I developed. The other is called Feature Engine, which is very popular. There's even a book written by this author. I highly respect her. And so it's a very good library. And RFE is a recursive feature elimination from scikit-learn. AutoFeat is a very good library, and they're also one of our competitors. And highly respect them. They generate tons of new features for using in synthetic features that they then use in their model for feature selection. Then there's something called sequential forward selection, backward selection, floating forward, floating backward. And then there's a library called, famous library called Boruta, and that's also got thousands of GitHub stars. So I decided to compare all of these libraries against featurewiz and see which one does, which is the best library for, I've taken an example data set. You can choose any other data set. You can copy this notebook, and basically instead of you have to just change one line of code, and you got to just say, instead of this data set, CSV, you just change it to some other name, and the notebook will run. So let me run this notebook. You can see here, featurewiz is done first. It takes 7 seconds. The next one is Feature Engine, smart correlated selection, and that takes only 1 second, so it's amazing. Feature Engine, and then it takes, there's another library from Feature Engine I call recursive feature elimination, and that runs for 21 seconds. I got AutoFeat, which is a famous library that generates features, additional features. This library created an unbelievable 1,300 new features out of the 26 features in the cars dataset. That is, I don't know how much, what percentage that is, but it is an unbelievable number of features that it created. And all I used was just feature engineering step 1. Suppose I used feature engineering step 3, which I did. It created 78,000 new features. So that is only for 26 features and 200 rows. Can you imagine if you were to give it 1 million rows, how many features, or 1,000 features, how many features it might create? So these are kind of interesting ideas, but I wanted to show how different people approach this problem. And then you got sequential forward selection, backward selection. Now, when you run all of them, I give you the time, and you look at the time, and then Boruta takes 24 seconds. And when you compare the methods, you can see that featurewiz, the mean root mean squared error is 2285, and I kept a held out test data set that root mean squared error was 1,133. So if you average these two, you got 1,700. And the number of features that featurewiz selected was 79. And AutoFeat selected, out of the thousands of features, it selected 183. And then Feature Engine selected 177. RFE selected 149. Boruta selected 5. If you look at all of these numbers, and I've sorted them by the average per method, featurewiz is the lowest error metric. Everyone else has got a higher metric, and the second closest one was AutoFeat, but it used 183 features. That is almost double the number of features that featurewiz uses. So you can see how, with basically taken one example. So I'm actually writing a paper comparing multiple data sets on this, and each time I will run the same test, and it's coming out that featurewiz is pretty good. So this is the good thing. So featurewiz does not create new variables, and that's the reason I mentioned AutoFeat. AutoFeat creates thousands of variables. Featurewiz does not do that. Featurewiz only selects from the existing variables. And the reason there are 76 variables in this case is that we used something known as one-hot encoding, and that's why you had 100 extra variables. But that was the same for all the methods. So every method was using the same number of features. I hope that's clear. We're not comparing one versus another. And SBFS are also pretty good. Let's take a look if it is pretty good. So these two are taking 15 features each. You can say that on the test RMSE, they've come out well, but the mean, which is the cross-validated score, they've done pretty badly. So, you can take your pick, but their goal is to try to come lowest on the both the mean, which is the cross-validated 5-fold cross-validation score on the trained data set, as well as use a model that was trained on train but tested on test, and see how well that model performs on the held out set. In both the cases, you can see that the lowest, one of the lowest is featurewiz, and it will also be able to do better on the cross-validation, which means that it generalizes much better. These features that featurewiz selected generalize much better than these others. So 1,000-point difference in a mean RMSE is not a joke. So I hope people understand that. Yeah, exactly, James. Yeah, it's easier. That's why I didn't want to compare. I'd like you to take this notebook and play with your own, favorite data sets, and then send me a note. I'm going to share my email. So the last one is called the Sulo models. This is a new set of classifiers are built in regressors. These actually take a single model, they train it on multiple folds, and they actually combine the folds based on the performance of the model on each fold, and they weight them differently. So if a model does better in one fold, it is weighted better than a model that does worse on another fold. So you can see that how that combination can be powerful. In this example, I'm going to stop here. It's pretty clear that you can see how you can take a plain old LGBM and then you can send it through Sulo, and then Sulo does better. And you can also see that Sulo finds the worst fold, whereas the other model doesn't have those features. But Sulo classifier has a feature that shows you the worst fold in your 5-fold data set. So you can focus on the fold 3, and you can call it X worst and Y worst. This is the worst X and the worst Y, and find out what's wrong with it using pandas data quality. So with this, I'll kind of stop here, but I hope I've given you an idea or flavor for how all of these can be, merged. All right. Thank you all, and I will send my this thing to folks to email here that you can see.
Great, thanks, Ram. I see quite a few questions in the chat. Not sure how you go through them yet. And just a remind, you can still post questions in the chat, or I actually already enabled the unmute. You can, if you prefer to speak, ask questions, or just open discussion, feel free to
feel free to unmute yourself. I can stay around for 5 more minutes, answer any questions. I usually love debates, so if anybody has the opposite view of what I'm proposing, would also love to hear that point of view.
Yep, that's a good idea. If anybody have different views, feel free to speak up.
Hi, Ram. Parnika here. Can you hear me? Yeah, yes. So I don't have any contradicting view, but there was this one question on on eliminating collinear variables, right? So the model or the library automatically selected 48 features on its own. So I was just wondering if we selected the eliminated ones and eliminated the selected features, will the performance be different? Any different?
Yeah, good question. Very good question. I've tested that, Parnika, and it does not give better performance in most cases, but in some data sets, the worst features that are rejected do add to the performance of the model. Not all of them together, but some. That is unfortunately the business that we are in data science. When you have 100 features, you cannot be really sure that the 48 features you got are the only best features. But if they do perform well, like I've shown you, both in cross-validation, 5-4 cross-validation, the average, as well as in the held out data set, hopefully that beats whatever else you got, whatever other combination you got.
Yeah.
Yeah, hope that helps.
Makes sense.
Yeah. Now, AutoFeat give you info on how it created a feature. Yes, it does. It's a pretty neat library. It creates thousands of features. It creates squared, cubed, sine, log, cosine. It's just unbelievable. That's how it creates 1,300 new features out of 26.
Would you recommend using these features for use cases where interpretability is important?
Yeah, great question. So one of the warnings in featurewiz is that do not use, featurewiz also has a feature engineering module. It's not as great as AutoFeat is, but it does create some extra features, I would say, additional features. If you turn on the feature engineering flag, you'll see that. I am not a big fan of creating huge number of features, but I do respect AutoFeat. I do understand or respect the sentiment behind it. You do sometimes need to create squared and cubed features. It's absolutely important. But do you have to create it every time? No, but AutoFeat is very useful. Yeah, you have to see AutoFeat came second to featurewiz, and that tells you something. featurewiz is without creating any features, using just the existing features and reducing them. AutoFeat took the opposite approach and it came second. So that tells you something. Could you please elaborate on the benefits of fine-tuning data? So you're asking me if this entire presentation was worth your time. I hope so. The benefits of fine-tuning data is what this presentation is all about. You have to clean your data. You got to select features from your data, and you need to select find the fold that's giving the worst results. Not every fold in 5-fold cross-validation is tripping up the model, but my Sulo classifier tells you in which fold it is tripping up the model. Once you know that, you can zoom in on that fold, use pandas-dq, compare that fold with the other fold, and see what is the difference. Once you find that, that's it. You have your answer, how to fine-tune data. So I hope that answers your question, Dishi.
Hey, Ram, great presentation. Can you hear me?
Yes, Umesh, yes.
Fantastic. Just one quick question on the time series kind of data. So I have two questions for you, maybe slightly out of the purview of the current presentation as well. So when you're fitting the time series data, and I was looking at your library, specifically the lazytransform part where you have the date and time converted into NLP variables. How would the time series data, date and time will be converted for interpretability? That's the first one. And then second question I have is, when you have gaps in time series data, is there anything that you suggest that comes from your experience is the best methodology for bridging the gaps?
Yeah, very good question. Umesh, this would take a long time. Let me quickly address first part of your question. A lazytransform takes something like 2017-06-07 and says it's June 7, 2017. And it splits it up as 2017, 06, and 07. That's it. And then it creates an additional feature saying it's a weekday, weekend, it's in summer, it's in winter, all of that. You should try it out, and then you'll see that if you send that model to an XGBoost or a thing, it'll actually perform better than if you were to take your time, and build a time series model. That's number one answer to your question. Number two answer to your question is gaps. That's a very good question. If you have gaps, all the ARIMA models, all of them, you know that, don't work well. Whereas if you were to use lazytransform, the gaps don't mean anything to a XGBoost because they've all been converted into numbers and your gaps disappear. So for XGBoost, that's just nothing. It's the same thing. Numbers are numbers. There are no gaps in numbers. There are gaps in numbers all the time. So it solves your problem. I hope that answers your question.
Yeah, that's brilliant. Just going back to the first question, just slightly additional point.
Yeah.
So when you use lazytransform, you said like the date and timestamps are converted into numbers. I've been working on one kind of a let's say a pilot project and trying to figure out where what we have done is we have given the minutes of the hour, let's say from 1 to 60, and then days of the week from 61 to 67, and then days of the month 68, so on and so forth, basically all the way going up to the year. And we found some fantastic outcomes coming out of that approach. Now, it is still very early stage. That's very recent kind of development that we have done, and I just wanted to get your views as to are we getting into some area where it could be let's call it a hallucination on our side?
No, I certainly assume that that's similar to what I'm talking about is converting data to numbers that the model can then understand and slice and dice them. That's exactly what you've done. But you've used a slightly different approach. But that's very reasonable assumption. It's not hallucination.
Perfect. Thank you so much. Really appreciate it.
You're welcome. All right. I think I can talk for hours about these topics and these libraries. I hope you enjoy the presentation. Please send me an email. You got my email on the screen here, and I'd be happy and welcome to talk to you offline. Thank you.